Hello, my name is Arpita P. Bharathi, and I'd like to present the work done by my colleague Monaldo Mastrolilli and I on a special class of the ideal membership problem. We will first go over the preliminaries, where we discuss 5 concepts that will allow us to describe the problem that we are interested in. We deal with polynomial ideals, where we consider multivariate polynomials with variables x1 to xn with rational coefficients. A set of polynomials I is called an ideal if it satisfies 2 conditions. The first is if it's closed under addition, and the second is that for a polynomial f in the ideal, any polynomial multiple of it belongs to the ideal as well. It's known that every ideal has a finite generating set, by which we mean that if the generators are polynomials f1 to fm, then by using properties 1 and 2 on the generators, we can produce the entire ideal. The polynomial ideal membership problem, or the IMP for short, is a well-known and fundamental problem that tests if an input polynomial f belongs to an ideal I, given the generators of the ideal. One way to test if f belongs to I is by using multivariate polynomial division. So we divide f by all the generators until we are left with a remainder polynomial r. Now, if it so happens that r is 0, then we see that f is a polynomial combination of the generators, so f must belong to the ideal. However, the remainder isn't unique and depends on the order of the divisors. So it is possible that f belongs to the ideal and we have a non-zero remainder. This is where the concept of Grobner basis comes in. A Grobner basis is a special generating set that ensures a unique remainder. So the remainder polynomial r is 0 if and only if the input polynomial belongs to the ideal. In general, though, the IMP is XP space complete, and as a consequence, the complexity of the Grobner basis is doubly exponential in the number of variables in the worst case. We concern ourselves with a particular kind of IMP that arises from combinatorial problems. Suppose we have a bunch of constraints from a language gamma on variables x1 to xn, where the variables are only allowed to take values from a fixed domain D. The goal is to decide if there is a common solution that satisfies all the constraints. This is the decision version of the constraint satisfaction problem, or the CSP of gamma for short. We deal with IMPs that come from ideals associated with instances of CSP of gamma. To be more precise, we take the solution set of an instance C of CSP of gamma and take the set of all polynomials that go to 0 at every point of the solution set. This, in fact, forms an ideal called the combinatorial ideal IC. In the general case, though, such ideals are called vanishing ideals. Now we're ready to define the ideal membership problem that we're interested in. The IMP associated with language gamma, what we call IMP of gamma, is the problem where for a given instance C of CSP of gamma, we decide if an input polynomial f belongs to the combinatorial IC, combinatorial ideal IC. We use IMP D of gamma when the input polynomial has degree at most D. IMP 0 of gamma is in fact CSP of gamma, where the constant polynomial 1 belongs to the combinatorial ideal if and only if the solution set of the constraints is empty. We are interested in the complexity of the IMP D of gamma. And to understand this, we must look into the complexity of CSP of gamma, which is determined by operations called polymorphisms. An M-array operation P is called a polymorphism of a relation R if by taking any m tuples from R and applying p coordinate-wise, we obtain a tuple that is also in R. If P is a polymorphism of every relation of gamma, we say that P is a polymorphism of gamma itself, or that gamma is P-closed. In our paper, we deal with the majority polymorphism, but I shall get into the details later. So the complexity of CSP of gamma, or IMP0 of gamma, over the Boolean domain has a nice dichotomy result, that it is polytime solvable if gamma is closed under one of 6 polymorphisms, including the majority polymorphism. Otherwise, it's NP-complete. A dichotomy theorem for complexity of IMP0 of gamma was established in 2006 for a 3-element domain, and in 2017 for any finite domain. Recently, it was found that the complexity of IMPD of gamma also has a nice dichotomy theorem for constant D, that IMPD of gamma is polytime solvable if gamma is closed under one of 4 polymorphisms, including the majority polymorphism, else it is co-NP complete. So naturally, we are interested to see if a similar dichotomy holds for the IMPD of gamma over a finite domain, of course, considering D to be of constant size. This has applications in sum of square proofs. In 2017, Raghavendra and Weitz asked which kinds of combinatorial ideals have nice generating sets that can be calculated in polynomial time, because it ensures polynomial bit complexity of certain SOS proofs. It is also useful in some theta body SDP relaxations where you would have to at least solve IMPD of gamma. In this paper, we take the 3-element domain D to be equal to the set 0, 1, 2, and a particular majority polymorphism called the dual discriminator. First of all, a majority operation is a ternary operation that takes the value that appears most often. For the Boolean domain, there is only one majority operation, but this is not true for larger domains. The dual discriminator is a majority operation, and in case of 3 distinct inputs, it picks the first. We choose to study those combinatorial ideals that come from a language gamma, such that the dual discriminator is a polymorphism of gamma. For example, we have a relation that is a subset of D squared that has 3 tuples as shown. We apply nabla, or the dual discriminator, on these 3 tuples coordinate-wise, taking 2, 0 first. So along the first coordinate, we have the majority to be 0. And along the second, we have 3 distinct inputs. So the dual discriminator chooses the first, which is 0. So if nabla is a polymorphism of this relation, then it has to contain the tuple 0, 0 as well. We prove that for a finite language gamma over the domain 0, 1, 2, such that gamma is nabla closed, the IMPD of gamma can be solved in polynomial time for a constant D. This is a consequence of the fact that a Grobner basis of the combinatorial ideal can be found in polynomial time. We, in fact, prove that to find a Grobner basis, you only need to look in a set of polynomials G, where G has polynomial size. We first use the fact that the projection along any 2 coordinates of a majority closed relation is also majority closed. This allows us to focus on relations of arity 2 instead. In terms of vanishing ideals, by using some basic properties, we can express the combinatorial ideal as a sum of ideals. So we could roughly divide the proof strategy into 2 stages. The first, we took relations of arity 2 that are nabla closed. We were able to identify a Grobner basis of the vanishing ideals for each of those relations. In fact, we were able to easily find the reduced Grobner basis for these ideals. While a Grobner basis can include some polynomials that aren't quite useful, the reduced Grobner basis does not and is unique to the ideal. Second, we then took two ideals from stage one and examined the reduced Grobner basis of the sum of these ideals. We then came to the conclusion that we only have to look at relations of arity 3 in order to find the reduced Grobner basis of the entire combinatorial ideal. So we proposed a set of polynomials G of polynomial size. This set contained all polynomials that were in stage one. We only needed a few more polynomials to complete G. We then needed to prove that the reduced Grobner basis of the combinatorial ideal IC is a subset of G. So we can write the combinatorial ideal IC as a sum of ideals generated by Fi, where Fi comes from G. We prove that if we know Fi belongs to the ideal, so should a few other polynomials, which we call accompanying polynomials and are denoted by A of Fi. We then prove that for any Fi, Fj in G, the sum of these ideals here, which basically come from here, has a reduced Grobner basis, which is a subset of G. So these new polynomials will replace Fi and Fj, and the process continues until we reach a point where Fi's are replaced by Qi's, and the reduced Grobner basis of sum of any two ideals here is a subset of Q1 to Qb. So we'll take a look at what the set G looks like. We have classified G into polynomials of 4 types based on their degree. We have the domain polynomials, which restrict every variable to only take values from the 3-element domain 0, 1, 2. These are univariate polynomials of degree 3. Then we have some quadratic polynomials in at most 2 variables, all of which are in fact obtained from stage 1 as discussed previously. Then we have linear polynomials in at most 3 variables, most of which come from stage 1. Finally, we have the constants 0 and 1. 0 because all ideals contain 0, and 1 to indicate an empty solution set. So to conclude, the journey of proving dichotomy theorems for CSP of gamma took almost 30 years to go from the Boolean domain to a 3-element domain. So establishing the complexity of IMP-D of gamma for a 3-element domain might not be trivial at all. So we started by taking the dual discriminator, which is believed to be a good starting point in majority operations. We ask if there's a universal strategy to tackle ternary majority polymorphisms in general. We also believe that it could be possible to extend our results regarding the dual discriminator polymorphism to a domain with k elements, where we might only have to look at relations of arity k, just like how in this paper we only had to look at relations of arity 3. We leave open the complexity of IMP-D of gamma, and we hope for a dichotomy theorem for a finite domain. Thank you.